Okay, welcome everybody. We're happy to have Valentin Buciumas, who will tell us about PQ dualities.
Thank you. Thank you for the introduction and thank you for the invitation to speak. It's great to speak in New York virtually, even if I cannot visit New York at the moment. So today I want to speak about something that I call PQ dualities. And what is this? This is a way of connecting the representation theory of two objects in such a way that you might be able to infer some interesting results from one object just by translating results from the other object. And the two objects I'm interested in are p-adic groups on one side and quantum groups. P-adic groups are somehow very important because you want to study the representation theory because somehow it's related to the theory of automorphic forms, for example. While quantum groups appear in a different setting, so they're related to things like solvable lattice models or knot invariants or categorification and so on and so forth. So the main idea is to try to connect the representation theory of these two objects. And the way this will be done is via the Hecke algebra. So Hecke algebras are certain algebras which appear naturally in both settings. And via this Hecke algebra, we'll be able to connect these two representation theories. And the point is, we want to somehow, like, given a result for p-adic groups, we will be able to write down a similar result or an equivalent result for quantum groups. And the point of these equivalences is that sometimes it's easier to work in one setting than it is in the other. And then we can just translate the result from quantum side to the p-adic side, or maybe vice versa. So let's talk about the summary. Basically, first I'll try to introduce p-adic groups and explain some basic things about their representation theory and how they connect to Hecke algebras. Then I'll briefly introduce quantum groups and their associated Hecke algebras. And then I'll try to explain how to connect these two. Everything I do in the first three sections will be type A. So the group I'll be interested in will be GLR. And in the fourth part of the talk, if there's time, hopefully there will be, I'll talk about what can be done outside of type A. Okay, so this is the main idea of the talk, and so let's get started. Okay, so what are p-adic groups and why do we want to study them? Basically, we'll be interested in a group, in the F points of a group G. In general, G might be something like reductive split over F and maybe some other properties. But for the purposes of this talk, at least in the beginning, we'll just take G to be GLR. And F, the field we're working with, will be local it will be a local non-Archimedean field. And an example is just the QP, the p-adics. And then what we want to study is we want to study smooth admissible representations of G of F. So this means the representations will be complex. So it's not how we study, for example, modular representation theory, where we might have the F points of a group G, and then we study representations over F, over the field F. In this setting, we study C, like complex representations. Okay, so some notation. So F will be our local non-Archimedean field. And the example to keep in mind is QP. O will be the ring of integers. And for QP, this is just ZP. Var pi will be an uniformizer, which is just P. And V is the cardinality of the residue field. So this is the quotient of ZP mod P ZP. So in this case, the cardinality will be just P. And in general, V will always be a power of a prime. This will appear later on. So it's good to emphasize this, since, for example, V will never be a root of unity, but we'll see how V appears later on. Okay, and then we have our group G. We have T, the torus, B, the Borel. So the torus is just the diagonal matrices, the Borel, the upper triangular matrices, and then the unipotent matrices. Whenever I write T, B, and so on, I'm always referring to the F points of the group. Okay, so now let's talk a bit about the representations of G, how to build representations, and what are some like basic examples of such smooth admissible representations. So the easiest example is we want to study these representations for GL1. So a representation will basically be a character chi that goes from GL1 of F into C star. So basically F star into C star. Now the character is admissible smooth if it has open kernel. So that means if 1 plus pi to the ko is in the kernel for some k larger than 0. And a special, so these will be all the representations, and a special type of representation which will play a key role as we move forward will be characters that are unramified. So that means in this condition here, I choose k to be 1, and this is what I'll call an unramified character. So to understand an unramified character, the main idea is we can write any element in F as p to some power times something like this. And then this part will be in the kernel of chi. So we get rid of it. So we're only left with, this is a var pi. So we're only left with chi of var pi. We can pull the alpha out. So now chi of var pi will just be a complex number z. So the main idea of this computation here is that chi will be determined by a non-zero complex number. So this is in some sense the most simple representation of GL1. And this will allow us to build representations for GLR. Okay, so now for GLR, the representation theory is a lot more interesting, but what we'll do in this talk, we'll focus on something that's called, on a set of representations that's called the unramified principal series. So we've seen before what an unramified character is. Based on that definition, I can build an unramified character of the torus inside GLR. And this will be determined by a set of R complex numbers. And the way I build it is basically if I have R characters for GL1, I can build a character for GLR. So this character will take the diagonal T1 up to TR, and it will apply the first character to T1, the second to T2, and then so on, and just multiply everything. So this will be a character of T. Here, Z is, for our purposes, a set of R non-zero complex numbers. In general, you can think of Z as living in the Langlands dual torus over C. And using this character, we can build what's called the unramified principal series. And we do this by inducing, by using parabolic induction. So what this means is we extend chi to a representation of B, and then we induce from B to G. What we do is, in fact, what's called normalized induction. So here I write the definition of this induction, and there's this like chi B here, which is somehow a technicality that's maybe not too important. But essentially, if we disregard this, this should look like what regular induction is. And then G acts on this space by right translation. So this will be a representation of G. Okay, so this is the unramified principal series. It's very important. So maybe let's talk about some properties. Sorry, are there any questions? So feel free to stop me if there's any questions. Okay. So what are some properties of this unramified principal series? It's reducible. The one basic question you can ask is it reducible or not? It will generically be irreducible. So that means for most values of Z, the principal series will be irreducible. For example, for GL2, the principal series will always be irreducible outside of when Z1 mod Z1 divided by Z2 is in a set of two, can be two things. And I think those two things will be something like maybe square root of V and minus square root of V inverse, or something along those lines. And if you are if you study the representation theory of quantum affine algebras, then you'll find that this somehow this might ring a bell, and we'll see that this is somewhat related as we move forward. So we have this property that this is generically reducible. This is infinite dimensional, and in general, all these smooth representations will be, most of them will be infinite dimensional. It has k fixed vector. It has a k fixed vector, and this is another way of defining an unramified representation. So here k is just the maximal compact subgroup, or the O points of G. And it also, so not only does it have Iwahori fixed vectors, but all subquotients. So in the case when pi of Z is reducible, all subquotients of pi of Z will have Iwahori fixed vectors. And what is the Iwahori? The Iwahori subgroup is defined as follows. So you can define a projection map that goes from the O points, so from the ZP points of G into the FQ points of G, where the uniformizer gets mapped to 0, and the Iwahori will be just the inverse of the Borel. Okay. So all these representations that have Iwahori fixed vectors will be called tamely ramified. Okay. So now some general facts about these smooth admissible representation. The most basic example is the unramified principal series, which we've just discussed. All representations will be infinite dimensional, with some exceptions. So one exception is the following: given GLR, you may take the determinant of GLR, and then you may apply a character for GL1. So this will be a one-dimensional representation that's irreducible. And in fact, you can show that the only finite dimensional irreducible representations for GLR will be of this form. So take determinant and then take a character. And outside of that, everything else will be infinite dimensional. So what is not a smooth admissible representation? You may think of the following representation, which is finite dimensional. So GLR QP acts on QP to the R, and therefore it also acts on the algebraic closure of QP to the R. And it's a fact that the algebraic closure of QP is isomorphic to C. So essentially what this produces is a representation of GLR QP on C to the R. And you may ask, is this an example of such a representation? And the answer is no, it's not. And the reasoning why is that the problem is that this representation will not be smooth. Okay, so what are some other representations outside of these principal series? You have representations that are called cuspidals. These are somehow significantly more complicated to build, and understanding these cuspidals is part of what's called the local Langlands correspondence. So it's a very interesting area to study, but for the purpose of our talk, we'll mostly deal with these simpler representations, which are very important nonetheless. So an example why they're so important, it comes from the theory of automorphic forms. So if you have what's called an automorphic representation, this is a representation over the adeles, which will break up into local representations. So this will produce a representation of, say, GLRQP for all P's. And a representation is automorphic if all but finitely many of these local representations are unramified, which means they have a k-fixed vector. So this means, as far as automorphic representations are concerned, in almost all cases, we'll have to deal with these unramified principal series, or maybe a subquotient. Okay, so now let me introduce some more notation. So we will have some natural G maps, which are called intertwiners or intertwining integrals. So first, the Val group is the normalizer of the torus divided by the torus. This is what you might know as the finite Val group. In particular, for GLR, this is just the symmetry group on R letters, and it's generated by Si, where I is between 1 and R minus 1, subject to the well-known relations. Using this, for each element of this Val group, one may define intertwining integrals. These are certain maps that map principal series to principal series. So note that we may act with the Val group on elements Z by permuting factors. So this intertwiner IW will map pi Z into pi W of Z. It has a natural definition as an integral over an intersection of subgroups. This definition is not like 100% rigorous, since it doesn't work all the time, but it works most of the time, and then you can do some tricks to make it rigorous, like maybe something like analytic continuation and so on and so forth. A very important fact is that this is a G map, and you can see from the integral way of writing it. And these maps will satisfy the braid relations. So once I define I as I for the simple reflections, then I can define IW by composing these integrals. Okay, so now we'll be going, now we'll start talking about Hecke algebras. Are there any questions so far?
These braid relations, it doesn't factor through the symmetric group, right?
Actually, if you choose, if you renormalize these integrals, you can make it factor through the symmetric group, but it's somehow a subtle point. So a priori, no, it does not. Any other questions? Okay. Okay, so now let's talk about Hecke algebras. Generally speaking, if you want to study certain representations of G, you might want to use Hecke algebras. So in very large generality, we may define for every open compact subgroup D, we may define the Hecke algebra associated to it as follows. It's basically the compactly supported functions from G to C that are D bi-invariant. So basically functions that satisfy this relation. And And there is a general fact that if G acts on a representation V, then this Hecke algebra HD will act on the D fixed vectors in V. And we'll be focusing on two important examples where D is the spherical subgroup, so G of O, and where D is the Iwahori. And the main point is that what this allows us to do is, instead of studying infinite dimensional representations of G, we will most of the time or all of the time be studying finite dimensional representations of some algebra that we can build from G. So these will be all for what we're interested in. These will always be finite dimensional. Okay, so two important examples. The first is the spherical Hecke algebra. There is a theorem of Satake which says that the spherical Hecke algebra can be identified with these type of W invariant functions on the co-weight lattice. So this is the co-weight lattice or the lattice of the Langlands dual group. This also happens to be the same thing as the split Grothendieck group of this rep of G check over C. And what one can prove is that if V is irreducible and G acts on V, then HK will act on VK, so the K fixed vectors of V. And this will either be an irreducible representation of HK or 0. HK is also commutative due to the Satake isomorphism. So the dimension of this VK will be 1 or 0, since it's irreducible. So it's a lot easier to work with things like this than things like this. Now, what can be the problem? If V has a K fixed, if V is irreducible and it has a K fixed vector, then there is like a bijection between such V's and representations of HK. But if V does not have a K fixed vector, then HK is somehow useless in giving us any information about it. But what happens is that the unramified principal series will always have one K fixed vector. So if it's irreducible, then we're in good shape because HK will somehow tell us a lot about it, will identify it. But if this is not irreducible, if this is reducible, then only one of the subquotients will have a K fixed vectors and all the other will not. So it will tell us, HK will tell us something, but maybe not too much. Yeah. And yeah, so all unramified G reps will be a subquotient of some principal series. Okay, now the second important example is the Iwahori Hecke algebra. So it's the same thing as before, but now instead of K fixed vectors, we use I fixed vectors. And now there's a theorem of Borel and some further results by Castleman. And what the theorem says is that there is an equivalence of categories from a certain subcategory of G reps and finite dimensional representations of this Iwahori Hecke algebra. And on the objects, this equivalence of categories just maps I to the I fixed vector, sorry, it maps V to the I fixed vectors of V. So now what exactly is this category? It is all the smooth admissible representations of G that they're generated by their Iwahori fixed vectors. So essentially all the representations will have, if you think of what are the irreducibles here, there'll be all irreducible representations that have an I fixed vector. So what is interesting about this is that this is an equivalence of categories, and it also has many interesting properties. So for example, it is what one might call a tensor functor. What this means is the following: you may if you consider all representations of GLR for all R at the same time, you have this induction operation on them. So what you do is you induce from GLR1 cross GLR2 parabolically. So that means you first extend to the parabolic and then you induce to the big group GLR1 plus R2. And then I haven't explained what the Iwahori Hecke algebra is, but there is also an induction process on it. And this will map induction to induction. Okay, so I think I've vaguely explained this. Okay, so something I haven't written down, but it's true, and it's a result of Castleman. All subquotients of the unramified principal series will have Iwahori fixed vectors. So what this tells us, why this is useful is because we can study this universal principle, this unramified principal series, by just looking at the Iwahori Hecke algebra. So this will tell us everything we want to know about that representation. So for example, if you're interested in things like what is the composition series of such unramified principal series, there is, you know, a representation here, and we can just study that, the composition series of that representation, and we're done. I haven't told you what the Iwahori Hecke algebra is yet. It is what some people called the affine Hecke algebra. And we'll get to the affine Hecke algebra in a moment. And this will depend on some V. So the affine Hecke algebra depends on some Q or some V maybe. And that Q or V will be related to the V that we defined in the beginning, which is the cardinality of the residue field. Okay, so this is a brief introduction to p-adic representation theory and Hecke algebras. So now I'll go and talk a bit about quantum groups. Are there any questions so far?
Yeah, just one quick question. So to be clear, you're sticking to looking at principal series. You're not looking at general parabolic induction from
I'll
blocks,
briefly
right?
mention, so this Borel-Castleman equivalence of categories can be generalized to different settings. And I'll briefly mention something outside of the unramified principal series, but yes, I'll focus with I'll focus on the principal series for most of the talk.
Okay, thank you.
Okay, so now let's talk a bit about quantum groups. I'll be a bit vague. So what happens is you can quantize, and quantize is, I'm not using it in any rigorous way. So you can quantize two objects. You can quantize the group algebra of a Val group and build what's called maybe a finite Hecke algebra. So what this means is, in our setting, the finite Hecke algebra will be generated by some TIs instead of SIs. They will satisfy the same braid relation and commutation relations. But now instead of the SI squared, we'll have a quadratic relation that looks like this, that involves some indeterminate or complex number Q. This will be the finite Hecke algebra. And maybe not similarly, but you can also quantize the universal enveloping algebra of semi-simple Lie algebra. So for UGLN, from UGLN, I can build a quantum group UQ of GLN. And this can be defined by some generators and relations, which I won't write. And what happens is that somehow the representation theory of U of GLN and UQ of GLN is very similar. So you have the same irreducibles, the same tensor product, like Littlewood-Richardson coefficients, so on and so forth. But there is, well, and of course I'm talking about when Q is not a root of unity. But there is a lot more structure for this quantum group. So in particular, you have some interesting R matrices. You have, instead of working with a symmetric monoidal category, you'll be working with a braided monoidal category. This will allow you to build, for example, knot invariants by using some theory developed by Reshetykhin and Turaev and other people. So on some level, these two objects are very similar, but this actually contains more information and more structure. Okay, so one way to relate these two objects is via Schur-Wall-Jimbo duality. So in the classical case, we have the following double commuting action, which produces many interesting results. So GLN, and therefore its universal enveloping algebra, will act on some defining n-dimensional representation Dn. And therefore, it will also act on the R tensor product of this representation. And then we can act on the right by the symmetry group. And the way the symmetry group acts is the generators Si will simply flip the ith and I plus 1 component of Dn to the R. And this double commute, and this is a double commuting action, and we can quantize it. So what this means is I can replace U by UQ, the quantum group UQ, and I can replace the symmetry group by the finite Hecke algebra. Now, the generators of this Hecke algebra will not act by simple permutation, but rather by a more interesting map, which is called an R matrix. And from this setting, we can eventually build a functor called a Schur-Wall functor that relates representations of this Hecke algebra with a certain subcategory of representations of the quantum group. So what does this R mean? It means degree R representations, which essentially means something you might find living inside this R tensor product. And this functor is very explicit, can be explicitly written. And it has many interesting properties. It's exact, it's monoidal. So on this finite Hecke algebra, we have an induction we can induce from two smaller Hecke algebras to a larger one. And on the quantum group side, we have a different type of we have what's called a tensor product. So basically, we can just tensor product representations. And what this functor does is, if we apply it to an induction, we'll obtain a tensor product on the UQ category of representations. Also, this functor is an equivalence for large enough n. So it's not always an equivalence, but as long as you work with a large quantum group, this will become an equivalence. And it's easy to see why it's not always an equivalence in this very simple example where we work with the Hecke algebra of rank 1. So basically, HQ2 will be generated by T1, and it will have two irreducible representations, the trivial where T1 acts as Q. So if you recall, T has to satisfy this quadratic relation. So if I'm looking at one-dimensional representations, T1 can act by Q or by minus Q inverse. These are the only two possibilities. So we'll have these two representations, trivial and sign. And what the Schur-Wall functor does is it will map trivial to the symmetric second power of Vn, and the sign to the exterior power of Vn. So you can just think about this. If it's not clear what the second symmetric power is in the quantum setting, you can just think about it in the classical setting. There is a way to define this in the quantum setting as well, but I don't want to bother defining it now. So here you can see that generally this will produce two different things, but when n equals 1, the exterior power of a one-dimensional space is 0. So when n equals 1, this will not be an equivalence. Okay, so this is Schur-Wall-Jimbo duality. There's also this side remark. I wrote this here because there's a similar way of defining Hecke algebras on the p-adic side as some endomorphism algebras, but maybe I don't want to go into this now because there's not that much time. Okay, so now what we can do is we can affinize this Schurval duality. What we do is we replace the finite Hecke algebra with the affine Hecke algebra. We replace the finite quantum group with the affine quantum group, or sometimes people call this the quantum loop group. In the non-quantum case, what I want to do is I want to take GLN, tensor Edmonton polynomials, and add a central extension, but I don't want to add a derivation. And then I want to quantize this object. This object will have some basic representations, which are called evaluation representations. So you pick how do you build such evaluation representations? You pick a representation of GLN, let's say the defining representation Vn, and then so GLN, we know how it acts on Vn, and then we add a parameter z, which tells you how t will act on Vn. T will act just by multiplication by z, and then in the non-quantum case, I want c to just act by 0. So we have these evaluation representations, V and Z. And then, for example, Jimbo constructed some affine R matrices that flip these two representations. So these are UQ maps that satisfy the braid relations and also a type of unitary condition. And they will most of the time braid between these two representations. So then what
does the unitary condition mean here?
It means something like R of Z1, Z2, R of Z2, Z1 will be a factor, or maybe two factors times the identity.
Okay.
And these factors will depend on Q, Z1, and Z2.
Okay.
And somehow they're interesting because I think they tell you things about when these two when this tensor product of representations will be reducible. And
okay, thanks.
Any other questions? Okay, so what Chari and Presley were able to prove is that you can enhance the previous Schurval functor to a functor that maps representations of this affine Hecke algebra to representations of this affine quantum group. Again, certain subcategory of such representations. And it has the same interesting properties. It's exact, it's monoidal. It maps induction to tensor product, and it's an equivalence for large enough n. Okay, so this was everything about quantum. Well, for now, everything about quantum groups, and now I'll try to relate the two settings. So if there is any questions now. Okay. Okay, so I haven't defined this, but we talked about an Iwahori Hecke algebra, and we talked about an affine Hecke algebra. And there's a theorem. So the reason I haven't defined it is that I was hoping people would know what at least one of these two is. And there's a theorem by Matsumoto which says that these two are isomorphic, assuming you set Q squared to be V. So Q squared is our quantum parameter and V is the cardinality of the residue field, or something like P. Okay, so now if these two objects are isomorphic, then we can basically try to see what happens if we compose these two functors that we talked about, the Borel-Castleman functor, which moved from representations of the p-adic group to representations of the Hecke algebra, and then the Chari-Presley functor, which moved to the quantum group side. So we can just compose this functor. It will go from here to here. It will have interesting properties. For example, it will be a tensor functor. It will map induction to tensor product. It will be an equivalence for large enough n. And here are some how this functor behaves on some simple representations. So it will map the GL. So this is the GL1 character or representation, chi z. It will map this to V and Z, the simplest evaluation representation that we talked about. Then it will map pi z, which is the unramified principal series. It will map it to a tensor product of Vn Zi. And this is so why does this hold? It's simply because pi z is obtained by inducing a tensor product of many chi z's. So this induction will get mapped to a tensor product. More so on the level of maps, it will map the intertwiner that we defined some time ago to the R matrix. The affine R matrix, so which braids between the ith and the ith plus 1. If you look at the tensor product, I'm being a bit vague here. There's probably a factor in front of the R matrix. It depends how you define it and so on, but let's not worry too much about that. So these are some interesting properties of this functor. Now, so there are certain generalizations of the Borel-Castleman functor. So the Chari-Presley functor will remain the same, but I can generalize this to certain settings. So one way to generalize it is as follows. You can actually work in greater generality. So you can break the representation theory of G. So not only the unramified or tamely ramified part, but all of it, all the smooth representations, you can break them into what's called Bernstein blocks. And there's some theory of many people, including Bushnell, Kuznets, and Heyermann. And what they were able to show is that you can find certain equivalences between every such block and some affine Hecke algebra. It's maybe not always a affine Hecke algebra. Sometimes it's maybe some tensor product of these affine Hecke algebras, but and it's a bit somehow technical, but you can do something for all other blocks. So this procedure is a lot more general. Another way to generalize this is you may replace your p-adic group G by what's called a metaplectic cover of G. And essentially you can still look at the tamely ramified part, and you can prove something similar. You can prove an equivalence of this type. And then the Hecke algebras will be the same. Yeah, so I'm being vague here, but you can generalize this to other settings. And it is actually in these settings that some interesting will be able to prove some interesting results. So now let me try to take you through some applications of this theory. So the baby application is the following. There's a theory on the quantum side. Most of the applications I have will be using something that's proved for the quantum side and moving it to the p-adic side. So the baby application is the following. There's a theorem by Hernandez. If I have k representations of UQGLN irreducible, then the tensor product will be irreducible if and only if a tensor product of either two of them is irreducible. Now, I can move this theorem to the p-adic side, and what this tells you is that if you have pi I a GLI irreducible representation, then this large induction will be irreducible if and only if these smaller inductions, all of them, will be irreducible. So this gives you, in general, induction is the most basic way of creating representations on the p-adic side. And this is a very useful result. And this was in the tamely ramified setting, this was known from before. But if you work in this more general setting with general Bernstein blocks, I believe this was not known before. It was not known in this generality. Okay, so this is one baby example.
Okay, I see a question. So this is really the core of this theorem is really going on the quantum affine side, not a Hecke algebra result. It's like, I mean, this functor, right? It passes from
Yeah. So my understanding is that so there's a theorem on the quantum side, on the Hecke side, and the p-adic side. My understanding is that this was first proved on the quantum side and not on the Hecke side. You may ask, why hasn't it been proved on the Hecke side? I'm not sure. I believe one reason might be because actual tensor product is slightly easier to work with than induction. But yeah, that's my understanding. So I don't know if this theorem being proved on the Hecke side. It doesn't mean you cannot do it, but maybe it's just easier in this setting.
I see. Thanks.
And in general, the moral maybe is, are people interested enough to prove something on one side? Are they willing to go through the effort? And what this does is, what this theory does is, if one person is willing to put in effort on one side, then you get the other two sides for free. And we'll see an example of this shortly, which is my work, I guess. Okay, so the second example is the following. So on the quantum side, you have another theorem by Hernandez. It says that if VI are, again, UQGL and hat irreducible representations, and if any two tensor products are cyclic or highest way representations, then the tensor product of many will also be cyclic. So this was a key ingredient that was used by Gurevich, Max Gurevich, to give a combinatorial answer to the following problem, which some people call the local Gangros-Prasad conjecture, or at least one of them, which is if you have a representation of GLR and one of GLR minus one, when is this home space non-zero? This is a relatively interesting paper by Max Gurevich. And this is done for, so not in the setting of tamely ramified, but for a general Bernstein block. And that's why we need that, that generalization. And now let me give a third application, which is my own work. So on the p-adic side, you may be interested in something that's called a Whittaker model or a Whittaker function. And you might want to compute dimensions of such Whittaker model. So let me briefly explain what's a Whittaker model. So a Whittaker model is some embedding of your representation into some space of n psi by invariant functions. But a different way to look at it is to consider the following space of Whittaker co-invariants. So for a representation of GLR, you may construct the space of Whittaker co-invariants, which is just the representation quotient this space. And here, psi is a non-degenerate additive character of your unipotent subgroup. These are pretty important in the theory of automorphic forms. And for GLR, there's a classical theorem of Rodier and Gelfand-Karsten, which says that if pi is irreducible, then the dimension of this object is 0 or 1. This is what's called a multiplicity one theorem. Okay. And we would like to understand if something similar happens in the metaplectic setting. But this actually doesn't happen. So for example, in the non-metaplectic setting, the dimension of the Whittaker model of the principal series will always be 1. But in the metaplectic setting, the dimension will be n to the r. So if this is irreducible, and most of the time it will be, the Whittaker model would be very, very large. So we already don't have a multiplicity one property. But what would be interesting would be if this is not irreducible, can I find for every subquotient, can I find the dimension of the Whittaker model? So this is a problem. And I want to restrict to the setting where these representations are tamely ramified, or in other words, they can be viewed as subquotients of the principal series. The reason is because the theory of cuspidal representations is not so well understood for these metaplectic groups. So now the theorem, which is a work in progress, is that for such a representation, the dimension of the Whittaker model is equal to the dimension of the associated representation of the quantum affine group, associated via this composition of Borel-Castleman or generalization of Borel-Castleman functor and Charry-Presley functor. So basically, this gives us a way to compute these dimensions. Why is this useful? The reason is because on the quantum affine side, there's this theory of Q characters that has been developed by Nakajima and Hernandez and other people. And from this, and it involves a lot of maybe geometry, like geometry of quiver varieties, so on and so forth. And from this theory, one can deduce these dimensions. And one can write them in terms of what's called affine Kazhdan-Lustig polynomials. So basically what this theorem does is it actually computes this dimension of Whittaker coinvariance. And the way it does it is by moving it to a problem on the quantum side, which has been solved. This problem on the quantum side is actually very hard. So Nakajima had to develop a whole lot of theory to compute these characters and therefore these dimensions. It involves Kazhdan-Lustig combinatorics and so on. So I think the main point I want to make is that by moving between these, between the p-adic side and the quantum side, you're able to maybe not have to do the same amount of work, but get some very strong results. Okay, so this is the theorem. How do we prove the theorem? Basically, there's two main ingredients. One, there's a generalization of a result of Bernstein and Zelevinsky, which says that all these tamely ramified representations will appear as the kernel of some intertwiner. And the second is these intertwiners will induce maps on these spaces of Whittaker coinvariance. And this is a result joined with Dan Bump and then Brubaker, that we may identify these intertwiners with certain R matrices. So this is very vaguely speaking the main idea. Now, a very immediate corollary is that if n is larger than R, any tamely ramified representation will have a non-trivial Whittaker model. This is somehow very easy to see from this setting. And it's a result that, as far as I know, wasn't known before. It's easy to see because if this happens, then the Charry-Presley functor is an equivalent. So you get something that's non-zero. Okay, so these are the main applications. So you might have a very basic question. Everything I said is for GLN. What happens if we work with other groups? And this was the point of the fourth part of my talk, which I don't have time to go through. But let me briefly say in like 1 or 2 minutes what's happening there. Essentially, everything connecting the p-adic side to the Hecke side can work for general reductive split group in the tamely ramified setting and in other settings as well, maybe with some problems, but not too many problems. So let's say p-adic to Hecke works all the time. Now, what happens to Hecke to quantum? And you can see that you do not have a, like, you don't have the generalization that you might immediately think of. So let's pick, for simplicity, let's work with the symplectic group. So the Hecke algebra will be the type C Hecke algebra, and let's work in the finite case. What happens is you cannot relate the representation theory of this Hecke algebra to the representation theory of quantum SP2N. But what happens is, turns out, is there's this theory of quantum symmetric pairs. So there will be such a functor that relates the type C Hecke algebra with a quantum symmetric pair. What is this? It's a subalgebra of the quantum group of type A. And it has some interesting properties. It's co-ideal, which means the co-multiplication will map UQC into UQC tensor UQ. So if it were just a subcoalgebra, you would have a C here, but you don't have a C. You have to use the full quantum group. And what this means is that if you have a representation of this co-ideal and a representation of the full quantum group, their tensor product will be a representation of the co-ideal. And this, as far as our setting is concerned, this makes sense because on the Hecke side, you can induce from type C tensor type A into type C. And the reason why is because, I don't know, you might want to look at the thinking diagrams and you can see that this is a subalgebra here. So basically you want to preserve this structure. So you want this induction to get mapped to something like a tensor product between type C and type A. And this induction is also natural on the p-adic side. So you may induce from SP times GL into some larger SP, but not from SP times SP into a larger SP. So in the affine case, so in the finite case, this is some recent theory by Huanjun Bao and Wei-Chang Wang. There's also some, for example, papers by Eric and Strobel that do some similar stuff. In the affine type, not much is known. There's a paper by Chen Guai and Ma. We don't know, for example, equivalence, if there an equivalence of category holds. We don't know much about these representations of this quantum affine symmetric pair. We, for example, don't even know the classification of irreducibles. So there's a lot of work to be done. And I think partly because these quantum affine symmetric pairs, people just haven't studied them. I think if you study them, you can find interesting things, but people haven't. So this type of equivalence, I think one of the main ideas is that in the future, you might be able to maybe move type C results from the p-adic side to the quantum side via this type of theory. Okay, I'll stop here. Sorry for being over time.
Thank you very much.
Yeah.
Questions for Valentin? So, oh, sorry, go ahead.
No, sorry. So are there any ideas of what happens on the normal p-adic side to distinguish representations? What that looks like on the other side?
So, sorry, can you remind me what's a distinguished representation? What do you mean by?
Yeah, like representations that have non-zero invariant functional by some subgroup, let's say of GL. What that translates to on the other side?
I'm not sure.
Okay.
I can say it seems a somewhat general condition. So there might not be a good answer, but I'm not entirely sure.
So the representation theory for the p-adic group for type C is known, and so now your point is that you now want to transport from p-adic to quantum for these quantum symmetric pairs.
Yeah. So that's a possibility of something you might be able to do. Yeah.
Awesome. And
I mean, there are problems, like as I mentioned. For example, you have this Spherical functor, but this is not known to be an equivalence. It's not known. There is some work to be done, but yeah, I think the idea would be that, yeah.
And this functor, which you called on the previous slide, FSW for, I guess, Scherr-Weil,
Yeah.
That who defined that functor, or is it just kind of clear from the type A case?
You mean this functor in type C?
Yeah.
Bao Wang, I think, were
did
the
they?
first to define it. I think it was also maybe implicit in a paper by Eric and Stroppel, but I think it was Bao Wang.
I see. So on the right hand side, right? So you're talking about quantum groups for generic Q. If
Yes.
you replace Q with a root of unity, is it known at all if what you should do on the p-adic side? Should it correspond to like some like loop group or something, or?
I don't think it corresponds to anything. I mean, immediately it doesn't correspond to anything. So you're very. I wrote somewhere that so you have to set this v equals q squared. You have to have this condition. And outside of that, I'm not sure if much can be done. I think there might be some interesting things at the roots of unity happening, but they won't be immediate.
Okay.
For example, there's this work by Gates-Corey on the geometric side, which I don't really understand. But for example, he relates certain generalizations of p-adic groups to maybe non-quantum loop groups at a certain level, and these will be related to quantum groups at the root of unity. So it might be that in that setting you might relate affine quantum groups at the roots of unity with p-adic loop groups.
I see.
But this is I don't see any immediate condition. So there might be interesting stuff happening, but I don't see an immediate condition.
Okay, thanks. Do you know even if is there a classification? I know you probably work on the p-adic side more, but is there a classification of the quantum affine algebras at a root of unity, the irreducibles?
I think for GLN, yes, and I think it might be due to Charlie and Presley.
I see.
If you work in the non-quantum setting, you definitely have you understand irreducibles and their characters. There's some loosely conjecture that holds. If you sorry, no, maybe disregard what I just said. So for quantum groups at unity, I think some things are known, including the classification of irreducibles by Charlie and Presley in the GLN case. But I don't think generally it is known, and I don't know if characters are known, for example, for like Q characters.
Okay, yeah, I see. Yeah, I can imagine the character question is out of reach right now. I didn't know you know the classification.
Yeah.
Thanks. Other questions?
I think in some cases the characters are known.
For quantum affine at a root of unity?
Yeah, I think Charlie and Presley did this. Yeah.
Okay.
Maybe not for general class, but for some they can. Yeah. They have a notion of quantum Frobenius, and I think the image of that they can classify.
Thanks. Okay. If there are no further questions, let's thank Valentin again. I'm going to stop the recording.
Thank you for having me here.